Hello students, so let us discuss the effect of parameter variation on our torque slip characteristics. Okay, so effect of parameter variation on torque slip characteristics of our induction machine. So what do you mean by parameters? So we have the parameters for our torque equation as proportional to, so I am taking the proportionality G equal to S E2 square R2 by R2 square plus Sx2 whole square. So these are the parameters based on which our torque will change. Okay, so I have to change each and every parameter and see how our torque slip characteristics are behaving. Okay, so I have to change each and every parameter and I have to see how the torque slip characteristics of our 3-phase induction motor are changing. Okay, so for that I am considering our starting torque here. So I have to see the variations in our torque slip characteristics, so that I have to consider starting torque, maximum torque and slip at maximum torque. Okay, so let us see. This is the expression for our starting torque, which is equal to 180 by 2 pi ns E2 square R2 by R2 square plus X2 square. Okay, so at the starting time, at the starting of our motor, this is the starting torque. So the torque at starting is called starting torque, right? So at the time of starting, I have already told you the rotor resistance is in the order of 0.2 to 0.3 ohm per phase. Okay, the rotor resistance at the starting of our induction motor is around 0.2 to 0.4 ohm per phase. Okay, if you square this 0.2, what will be it equal to 0.04. That means our R2 is very less compared to our X2. Okay, the value of rotor resistance at the time of starting is very less compared to our rotor leakage reactance. So I can replace this R2 square by X2 square with only X2 square. Okay, I can remove the R2 square component because it is very little. Okay, I can remove it and I can replace the entire denominator as X2 square. Okay, now let us see how our maximum torque, starting torque and our slip at maximum torque will behave for each and every parameter variation. Okay, so let us see. All R2, E2, X2 all are per phase quantities. Okay, now let us see the effect of our rotor resistance. Okay, effect of our rotor resistance on the torque slip characteristics. First thing is effect of R2. Let us see how our rotor resistance will affect our torque slip characteristics is our aim here. Okay, so let us consider our starting torque, okay, which is proportional to our rotor resistance. Okay, our starting torque is directly proportional to our rotor resistance. Okay, and what about our maximum torque? Our maximum torque is not a dependent quantity of our rotor resistance. That means our maximum torque is independent. That means it is constant for any value of our rotor resistance, right? Now let us see our maximum slip at maximum torque condition, that is S max, which is given by our rotor resistance by rotor leakage reactance. So here the slip is directly proportional to our rotor resistance. That means our slip is directly proportional to rotor resistance. Okay, whenever if I increase the rotor resistance, which is possible in our slip ring induction motor, right? Whenever I increase the rotor resistance, our starting torque will increase. Okay, whenever I increase the rotor resistance, our starting torque will increase, and maximum torque is constant because it is independent of our rotor resistance. And what happens to our slip at maximum torque condition? Whenever I increase the rotor resistance, our slip at maximum torque condition will also increase. Okay, that means our starting torque and slip at maximum torque will increase when I increase the rotor resistance. So let us see the behavior of our new torque slip characteristics whenever I increase the rotor resistance. That means here our starting torque is increasing. That means this is my new starting torque. This is my new starting torque. I am representing it as TST dash. Okay, this is my rotor. This is my starting torque. Whenever I increase the rotor resistance R2 dash, this is my increased rotor resistance, which is greater than initial one R2. Okay, I have increased the rotor resistance from R2 to R2 dash. Now my starting torque has been increased from TST to TST dash. And what happens to maximum torque, which is constant? It is constant. That means it is on this line. Okay, and what is happening to our slip at maximum torque? Which is increasing. That means slip is increasing from 0 to S1. Initially it was SM. Now it is increased to SM dash. Okay, due to increase in rotor resistance, our slip is increased from SM, which is here. This is my SM. Okay, now it is increased to SM dash. That means the increment of slip is left side. That means I consider this is the point where my slip is increased to Sm dash. Okay, this is corresponding to our R2 dash. R2 dash. This is R2. This is corresponding to R2. This is our corresponding to R2 dash. R2 dash is nothing but our R2 plus some external resistance, some additional resistance. Okay, this is nothing but our Re. If I add Re to R2, it become R2 dash. Because of R2 dash, our starting torque changed. Our slip at maximum torque is also changed. That means, let us see how our torque slip characteristics are behaving. Hello students. So let us see the variation of rotor resistance on our torque slip characteristics. So you can see the relation between torque and resistance are like this. Okay, our starting torque is directly proportional to our rotor resistance. Okay, our starting torque is directly proportional to rotor resistance. Actually, its starting condition, we are going to add external resistance in slip ring induction motor. So our total rotor resistance will be R2 plus our external resistance. In slip ring induction motor, we are going to add this external resistance Re at time of starting, so that we can increase the starting torque. Okay, so our R2 will be equivalent to our R2 total at starting condition. Okay, and what is the relation between T max maximum torque and our rotor resistance? I think there is no relation, so it is not a dependent quantity of our rotor resistance, so it is constant. Okay, our maximum torque is a constant value irrespective of our rotor resistance value. Okay, now let us see the relation between our slip at maximum torque and our rotor resistance. Okay, so here we can see a direct relationship between slip at maximum torque and rotor resistance. Okay, so this is the relation between slip and rotor resistance, and this is the relation between maximum torque and our rotor resistance, which is constant value irrespective of our rotor resistance. Okay, and our starting torque is directly proportional to rotor resistance. Okay, so whenever I increase the rotor resistance at the time of starting, our starting torque will increase because it is directly proportional. Okay, whenever I increase the rotor resistance, our starting torque is increasing, and irrespective of increase in rotor resistance, our maximum torque is not responding because it is constant. Okay, the maximum torque irrespective of any value of rotor resistance is constant, and slip at maximum torque is also increasing with increase in rotor resistance. If I keep on increasing the rotor resistance Re at the time of starting, okay, my starting torque will go on increasing. Okay, so this is the idea. So I will increase the Re value such that our total resistance of the rotor, this is my total resistance R2 total, equal to our rotor leakage reactance. I have to increase the Re value such that our total resistance in the rotor should be equal to rotor leakage reactance. Okay, so that is it starting to get the maximum starting torque. Okay, I have to increase the external resistance value to get the maximum starting torque. So let us see, I have increased the rotor resistance, I am considering it as R2 dash. Okay, increased the rotor resistance which is greater than our initial value R2. Okay, this is my condition, first condition. Okay, so now what is the behavior of our parameters? So TST dash is also increasing, that means TST dash is TST starting torque is increasing. So I am mentioning TST dash is greater than its initial value TST. Okay, and T max is constant. Okay, T max is constant value. And what is the behavior of our slip at maximum condition? It is also T max dash is constant and slip at maximum torque is greater than slip at maximum torque initially. Okay, so this is the relation. Now let us see the curve, torque slip curve, how the torque slip curve is varied now due to increase in rotor resistance. Our starting torque is increased, so I can make it as like this. So this is my starting torque, increased starting torque, so I can make it dash. This is my increased starting torque due to increase in rotor resistance. Okay, now what about my maximum torque? It is somewhere on the maximum torque line. Okay, it is constant value. Okay, and what about our slip at maximum torque? It is increased, that means slip is increasing from left to right, sorry, right to left. Okay, this is the increase of slip and this is increase of speed. Okay, this is slip, this is speed, both are inversely proportional to each other. If slip increases, our speed decreases. Okay, if slip decreases, our speed will be increased till synchronous speed. Okay, now our slip at maximum torque has been increased due to increase in rotor resistance. Okay, initially it was here, now it is increased, means it is this in this area. Okay, this is the portion of increasing. Okay, I consider this as Sm dash. Okay, due to increase in rotor resistance, this is my new slip at maximum rotor condition, maximum torque condition. Okay, and what about our Ns? Ns is constant irrespective of our rotor resistance because it is not a dependent quantity of resistance. Okay, Ns is constant. Okay, it is constant here. So Now let us draw our torque slip characteristics with increased rotor resistance. Okay, so this is my starting torque, this is my maximum torque, and this is my slip at maximum torque, and this is my synchronous speed. Okay, I am going to draw the torque slip curve. You can see, okay, this is my new curve, new torque slip curve. Okay, due to increase in R2 dash. If I furthermore increase my rotor resistance, okay, I increase the rotor resistance further. So what will be the behavior of our components? This is constant, this is increased. Okay, now this is further increased. This is my SM double dash due to furthermore increase in the rotor resistance. So this will be my TST double dash. Okay, this will become my maximum torque position, and our synchronous speed is constant irrespective of any rotor value. Okay, now I am going to draw the torque slip characteristics for this thing. Okay, this will be, this was for R2 dash, this was for R2, and this curve is for R2 double dash, which is greater than this value and which is greater than this value. Okay, and I am furthermore increasing the rotor resistance R2 triple dash. Okay, the parameters will get hyphens here, primes here. This is my third curve slip at maximum torque condition. So this will be my SM triple dash. Okay, this will be the maximum torque. Okay, my TST triple dash. Okay, you can see further I have furthermore increased the rotor resistance. You can see the starting torque was initially here, it is increased to this point. That means it is almost near to my maximum torque point. This is my maximum torque point. Okay, our starting torque is almost equal to maximum torque. That means if I keep on increasing the rotor resistance, okay, if the total rotor resistance R2 total, okay, which is equal to R2 plus change RE, this is variable one. If this value is equal to x2, then our starting torque will be equal to my maximum torque here. The curve will be like this. Okay, if I keep on increasing R2 double dash, R2, our total rotor resistance to a value at which our total rotor resistance R2 total, which is sum of our R2 and external resistance, is equal to x2, then I am going to get my starting torque equal to my full load torque, my maximum torque. So at this condition my starting torque will be equal to our maximum torque. So by increasing the rotor resistance we can increase the starting torque up to maximum torque. Okay, so this is the idea. Okay, you can see this was the initial rotor resistance. By adding some external resistance, the curve is shifted to this position, and if you furthermore increase the rotor resistance, our curve is shifted to furthermore position, and if you keep on increasing this to R2 triple dash, okay, and if you furthermore increase this to R2 4 dash, okay, if we keep on increasing the RE value such that our total resistance equal to our total rotor reactance, our starting torque will be equal to, at this condition, okay, at this condition our starting torque will be equal to maximum torque. Okay, you can get the starting torque of the machine equal to maximum torque. Okay, it is possible by increasing the rotor resistance. Okay, so this is the idea. So each and every value are greater than previous value. Okay, R2 is less, R24 is greater than R23, R22, R21 and R2. Okay, so this is the concept of variation of rotor resistance on torque slip characteristics. Okay, so now let us see the effect of our supply voltage on our torque slip characteristics. That means let me consider effect of our supply voltage, which is nothing but E1 here, which is nothing but E2. Okay, our supply voltage is nothing but E2 here. Okay, so let us see our starting torque behavior whenever we change our supply voltage, which is directly proportional, right? Our starting torque is directly proportional to our supply voltage, and what is happening to our maximum torque, which is also directly proportional to supply voltage, and our slip is independent of our supply voltage. That means our slip at maximum torque is constant. Okay, these are the three important parameters to draw the torque slip characteristics: starting torque, maximum torque and slip at maximum torque condition. Okay, our synchronous speed is constant for given frequency, right? Our synchronous speed ns equal to 120 f by p, which is constant until and unless we change the frequency. If only frequency is changed, then only our speed of induction synchronous speed will change. Okay, so these are the parameters changes whenever we change the supply frequency. That means if I reduce the supply frequency, our starting torque will reduce. If I reduce the supply frequency, our maximum torque will reduce, but the slip at maximum torque is constant. Okay, so these are the changes when I change the supply voltage. Okay, so let us see the torque slip characteristics at effect of our supply voltage. Okay, because I decreased the supply voltage, E2 dash, which is less than our initial one E2. Okay, I reduce the supply voltage which is less than our initial voltage. So how the starting torque is behaving? It is reduced. This is my new starting torque corresponding to my reduced supply voltage, which is TST. Okay, that means our TST dash is less than TST. Okay, this is one condition. And what is happening to Tmax? Tmax is also reducing to some value, that is, this is my Tmax dash. Okay, that means our Tmax dash less than our Tmax. Okay, our maximum torque is also reducing to some value, and our slip at maximum torque is constant, which is Sn. That means, so the new torque slip characteristics of our induction machine, whenever we change the supply frequency, will be like this. Okay, so this is the new torque slip characteristics of our supply, our torque slip characteristic induction machine, whenever we change the supply voltage. So let us draw a load line. This is my load applied on the induction machine. Okay, I am representing it as TL. Okay, so this was the red color curve was initial one, that means the speed at which that red color is NR, and this blue color is whenever I change the supply voltage. That means the speed of our induction machine is now reduced somewhat. That means our NR dash is less than our speed of rotor before changing the supply voltage. Okay, you can see, because I reduced the supply voltage, our starting torque reduced, maximum torque reduced, and our speed of the induction machine also reduced. So this is the observation for effect of change in supply voltage. So now let us see the effect of change in supply frequency. Now let us see the effect of supply frequency, effect of change in supply frequency on torque slip characteristics of our induction motor. Okay, so before that, I have to consider the EMF equation of our induction machine, which is equal to 4.44 n pi max f. Here f is nothing but our supply frequency. That means our maximum flex is proportional to here E by S, which is nothing but my stator EMF, or which is also equivalent to my rotor EMF. That means this is the flex in the induction machine, which is dependent on our frequency. Okay, so what happens if the frequency of our system is reduced? I reduce the frequency of our system. Now let us consider this case number 1. Okay, so I reduce the frequency, so the flex in the air gap will increase. That means our flex is increased, that demands high magnetization currents from the supply, which is disadvantage. That means our increased flex is demanding high magnetizing current from the supply, which also results in high losses, high core losses in the machine. Okay, and if you increase the pi max greater than its saturation value, okay, if you increase the pi max by reducing the frequency beyond the saturation point, our core material in the induction machine will go to saturation position, deep saturation position. That means our core materials in the stator will go to deep saturation, and that will demand more saturation, more magnetizing current, and it may not come back to our linear operating position. That means our core material of our induction motor will go to deep saturation, and it will demands more magnetizing current, and it may not operate in linear fashion. Okay, let us see the BH curve is like this. Okay, like somewhat like this. Okay, if you increase the core flex beyond some position, okay, if this is my maximum saturation point, if you increase the core flex beyond this point, this will go to saturation. Okay, this saturation will demand more magnetizing current. Okay, and this may not come back to linear position, it will be some non-linear position. Okay, the saturated core may not behave like a linear core, and it will fail the operation of our induction machine. That means the saturated core may not behave in the linear like a linear core, and it will increase the demand of our magnetizing current, that will damage the windings due to the heat produced. So this is not desirable to increase our maximum flex beyond our saturation point. Okay, we are not supposed to increase the flex maximum beyond its saturation position. so that our machine will be in linear operation condition. Okay, for that I cannot reduce the frequency only, so for that I have to change the voltage and frequency such that our flex in the air gap is constant. That means if I have to reduce the frequency, I have to reduce the voltage also. Okay, this is nothing but variable voltage and variable frequency operation. Okay. If you have to operate the machine at reduced frequency, you have to reduce the voltage such that our flex is constant. That means our V by F ratio should be constant. Okay, V by F ratio should be constant, then only there will be no saturation of core material, which increases the loss in the core material. Okay, our V by F ratio should be constant. If you have to use the reduced frequency operation, you have to change the voltage also such that our V by F ratio should be constant. Okay, so for that, so the conclusion is, if you have to change the frequency of AC machine, you have to change the voltage also such that the V by F ratio should be constant, which will not allow the core material to go to deep saturation. That means our flex in the air gap should be constant. This is only possible when you maintain the V by F ratio constant. Okay, V by F ratio should be constant. Okay, so let us see, if we are changing the frequency here, so how can we keep the V by F ratio constant here? Here you can see our synchronous speed, which is nothing but Ns, is also a dependent of our supply frequency. Okay, our synchronous speed of our induction machine is also dependent of our supply frequency. So I consider Ns is also dependent of our supply frequency, which is directly proportional. Okay, so I am considering the parameters which are dependent of frequency here. Okay, let us see each and every parameter. First I take starting torque, which is proportional to here our supply frequency dependent is Ns, which is synchronous speed, and here E2 square nothing but V1 whole square P square by X2 square is nothing but X2 is a component which is having frequency in it. Okay, this is X2, right? X2 is having frequency component, so I can replace the X2 with F whole square. Okay, this is my starting torque in the form of frequency. Okay, so this is nothing but TST, starting torque, is proportional to V by F whole square into 1 by F. That means if you change, if V by F is constant, our starting torque is proportional to F 1 by F. If V by F is constant, our starting torque is inversely proportional to frequency. If V by F is not constant, our starting torque is proportional to 1 by F cube. That means 3 times of its initial value. Okay, our starting torque is inversely proportional to F if V by F ratio is maintained constant. If it is not maintained constant, the starting torque will be inversely proportional to F cube. Okay, and if let us consider the maximum torque. Okay, so let us consider the maximum torque now. So let us see the maximum torque here, which is also a dependent of 1 by F here, because it is having synchronous speed, and we can consider it as V square. But here it is having only one parameter, which is X2, so I consider it as V by F. So our maximum torque is proportional to V by F whole square. That means if V by F is constant, our maximum torque will be constant. Okay, if V by F is not constant, our maximum torque will be proportional to 1 by F square. Okay, so this is the parameter variation, frequency variation for starting torque and maximum torque table. So this is one important table. Okay, starting torque and maximum torque variation with respect to our V by F ratio. Okay, so let us see the torque slip characteristics variation with respect to our frequency. Okay, and we have to consider one more component, that is slip here. Okay, slip is also having one frequency component in the denominator. That means S at maximum torque condition is inversely proportional to supply frequency. Okay, this is the, so let me write the parameters here. TST is proportional to 1 by F times V by F whole square. This is one relation, and maximum torque is proportional to V by F ratio. This is another relation, and our slip at maximum torque condition is equal to inversely proportional to F. Okay, so let us consider two cases, that is whenever I increase the frequency and whenever I reduce the frequency. Okay, let us consider first one, whenever I have to reduce the frequency from its rated value. So first case one is reducing the frequency. Initially it was Fs, now I am reducing the frequency, that means our Fs dash is less than Fs. Okay, if you have to reduce the frequency, you have to change the supply voltage such that V by F ratio should be constant. Because I am reducing here, because I am reducing the frequency here, V should also be reduced. Okay, because flex is proportional to V by F. If I have to reduce the frequency, I have to change the voltage, supply voltage such that V by F ratio should be constant. Because I am reducing the frequency, I can change the voltage such that V by F ratio should be constant. That means our TST will be proportional to only 1 by F S dash here. Okay, and because I reduce the supply frequency, our TST will increase. Okay, our TST is increasing, starting torque is increasing. And what is happening to T max? Because I am reducing the frequency and I have to change the voltage also, so that our V by F ratio should be constant. So if I have to reduce the frequency, our T max is becoming constant here, because V by F ratio is constant. Okay, our maximum torque is constant because V by F ratio is constant. So what is happening to slip? Slip is inversely proportional to frequency. If I reduce the frequency, our slip will increase. So these are the changes in the 3 parameters here. So let us draw the torque slip characteristics depend using these components. So I am taking the T in the y axis and slip on x axis. This is initial condition which is on NR equal to 0, which is NR equal to NS. Okay, here our NS is also one dependent component of frequency, right? If you reduce the NF, our supply frequency also, sorry, our synchronous speed also changes. Here we can consider it as, let us see, TST starting torque is increasing, and our T max is constant, and S max is increasing, and NS is decreasing. These all are primes. Okay, these all are after changing the frequency. Initially the curve will be like this. This is the TST starting torque related to Fs, okay, and this is the NS corresponding to our Fs, okay. This is the slip at maximum condition corresponding to Fs, okay, and this is the maximum torque which is also constant for Fs and Fs dash. Okay, now let us see the curve after reducing the frequency. So what is happening to the starting torque, which is increasing? So our starting torque after reducing the frequency is increasing. That means our TST dash is greater than TST. And what is happening to maximum torque? It is constant. Okay, it is somewhere on this line, on this maximum torque line. Okay, and our S max dash is increasing. That means the increase is from 0 to 1. That means it is somewhere on this line. That means this is for Fs dash. This is the slip at maximum torque condition when I change the frequency to Fs dash. Okay, now this is the new slip at maximum torque. Okay, and frequency and the synchronous speed is reducing. That means this was an earlier synchronous speed, now it is reduced to here. This is my NS corresponding to Fs dash. Okay, now let us draw the torque slip characteristics of our new machine with changed frequency. Okay, this is my new torque slip characteristics of our induction machine when I reduce the frequency. Okay, our synchronous speed is reduced, slip at maximum torque is also reduced, and you can see the change in our rotor speed. Here it was initially here and it is improved to here. That means our NR dash, speed of our induction machine rotor NR dash is greater than NR due to the change in frequency. That means our rotor speed is increased. That means this is the relation, our rotor speed is increased when I reduce the frequency. Okay, this is regarding reduction of frequency. Now let us see the increase in frequency, how the increase in frequency will change the torque slip characteristics. Okay, initially it is changing torque slip characteristics like this. TST is increased, T max is constant, and S max is improved. Now let us see increase in frequency, how it is changing the torque slip characteristics. Now let us see how the increase in frequency is changing the torque slip characteristics. So before that I have to reconsider the flex. So before I was reducing the frequency such that our flex may go beyond the saturation point. Now I am increasing the frequency, so our flex will reduce. That means we need not to change the voltage here. We need not to change the voltage if you have to increase the frequency, because our flex is reducing. Initially we were fearing that our maximum flex may go beyond the saturation point and our core will get saturated. Now our maximum flex is reducing, so there will be no problem of saturation. Okay, that means I need not to vary the voltage here if I have to increase the frequency, because I am increasing the voltage, I need not to change the voltage, and I need not to keep the V by F ratio constant. Okay, so this is the, here frequency is the only component changing here. That means let us see, our TST will be proportional to, initially it was 1 by F and it is 1 by F square. Okay, our TST is inversely proportional to cube of frequency with V by F ratio not constant. Okay, we need not to keep the V by F ratio constant here. So what is happening to Tmax? Tmax initially it was constant because we have to keep the V by F ratio constant. Now it is V by F square. That means Tmax is now 1 by F square. Okay, what is happening to slip? Slip is inversely proportional to F here. Okay, if I increase the frequency, supply frequency, so what is happening? Our starting torque is reducing and our maximum torque is also reducing, and our slip at maximum torque is also reducing. And what is happening to the synchronous speed, which is directly proportional to supply frequency, because I am increasing the frequency here, our synchronous speed also increases. Okay, so because I am increasing the supply frequency, our synchronous speed, which is proportional to supply frequency, will also increase. So let us see the parameter variation. Our frequency variation Fs dash, which is greater than our supply frequency, is now changing our starting torque TST dash, which is less than initial one TST. Okay, our TST is now reduced and Tmax is also being reduced. Tmax dash, which is after frequency increase, is less than Tmax before increasing the frequency. So supply, our Smax is also reducing from Smax before. So all these are related to Fs dash. Okay, all these are related to Fs, because Fs dash is greater than Fs. So this is the parameter variation here. Okay, all these left side components are related with respect to Fs dash, which is greater than our Fs. So all these right side components are with respect to our supply frequency before increment. Okay, and what is happening to synchronous speed? Our Ns dash with respect to Fs dash is now greater than Fs. Ns dash, Ns it with respect to supply frequency. So because I increased the frequency, this is the effect of parameters on the torque slip characteristic. So now let us see the behavior of torque slip characteristics with these changes in the parameters. Okay, now I am going to see the effect of these parameters on our torque slip characteristics. Okay, now this is my slip at 0 and our NR will become Ns. Okay, this is my slip at starting is 1, NR equal to 0. My speed is increasing and slip is reducing. Okay, this is my torque. Okay, initially the torque slip characteristics before increment of frequency are like this. Okay, this is linear curve. This is my condition. This is my torque slip characteristics with respect to supply frequency. Now I have increased the frequency to Fs dash, which is greater than Fs. Now let us see the behavior of starting torque is reduced. That means our starting torque is, initially it was here, now it is reduced. That means this is my new starting torque with increase in frequency. And what is happening to maximum torque? Maximum torque is also reduced from initial value. So this is my new maximum torque line. This is initial Tmax. This is Tmax dash corresponding to Fs dash. This is corresponding to Fs. Okay, our maximum torque is also reducing and starting torque is also reducing due to increase in supply frequency. Okay, so what is happening to slip at maximum? This is my slip at maximum before change in the frequency, that is Fs corresponding to Fs. So the speed of the machine will be Nr at Fs. Okay, now let us see the change in the torque slip characteristics with change in the parameters here. Okay, so initially it was TST and it is somewhat reduced, and let us see the slip at maximum torque is also reduced. That means this is 1, this is S, that means it is somewhere here. This is my Sm dash with respect to FSE, Fs dash. So this will be my Nr dash. You can see that Nr dash is near to synchronous speed. That means our speed of the rotor is increased due to the increase in frequency. And you can see our synchronous speed was initially at this point, now it is increased to some extent. Okay, this is my Ns dash corresponding Fs dash. This is my Ns corresponding to Fs here. This was Ns corresponding to Fs. This is Ns corresponding to increase in frequency. Now let us draw our new torque slip characteristics with increase in frequency here. So this is my new slip at maximum torque condition. Okay, this will be like this. Okay, if I have a torque on load torque on the machine is on the red line. If I have a load torque as this much, okay, what is the behavior of speed of induction machine? Okay, this is initial one, now this is my final one. So you can see this is my NR, this is my NR dash for this load. Okay, this is the load, this is the speed. That means NR dash for load TL is greater than NR for TL. Okay, in order to supply the same load before and after increment in the frequency, our speed of the induction motor is increased. In order to supply this TL, our speed is increased from this point to this point. So these are the observations. Okay, these are the changes in the torque slip characteristics according to changes in the parameter variation. Okay, so this is about effect of parameter variation on our torque slip characteristics. Okay, thank you.